Correct answer is A, attractive. In north and south poles. Yes? Okay. Ampere's law. This is like Gauss's law. This is the shortcut. Okay. Um, so this is a line integral that is enclosed. That's what that symbolizes. Um, and this is equal to um, enclosed, right? Enclosed, enclosed. It doesn't, but I'm trying to do my best. Is it? Thank you. Thank you. Enclosed. Okay. In this Amperian loop. Okay. So with Gauss's law, we did, this was a surface integral. So we made a bubble. Okay. This and that bubble could look in a lot of different ways. A lot of times it was spheres. It could have been a cylinder. This is just a loop. A lot of times it's a circle, but it doesn't have to be. Okay? Is everybody all right with that? Like you got an area, this is a line, like linear. Okay? And so we are, uh, so it has a similar format. Okay? And this is 4 pi times 10 to the negative 7th. Okay? So here, if it is, if the magnetic field is perpendicular to the path that we're integrating, that is 0 because it's a line integral. And we're looking for the component of the magnetic field that is parallel to the path that we're integrating. Okay, so this would be 0. This would be a maximum where here the magnetic field is always parallel. The component is parallel to the path that we're integrating. Okay, so this would be b times the length of whatever this path is. Good with that? So those are the extreme cases. So what we're going to try to do is we're going to try to draw our Amperian loops so that the magnetic field is either perpendicular to the path or parallel to the path. That would be bueno, muy bueno, because then we don't have to do calculus. Okay, good with that? So this would be the simplest example. Remember we did a point charge with Gaussian Gauss's law, and we proved like, hey, check it out. The electric field is equal to 1 over 4 pi epsilon naught over charge over radius squared. Remember that? Okay, this is that same type of, this is like as simple as you can get. Like we did Gauss's law, we did area is equal to charge enclosed over r squared, and this was 4 pi r squared. Oops, sorry. Nope. That's epsilon naught. You brought that over. Gauss's. Yes. Okay. So Ampere's law is just a single wire with current flowing through it. So we're going to draw our Amperian loop. It's not a sphere, it's just a loop, just a circle. Okay. Has a certain fixed radius. And we're saying at that radius, the magnetic field is constant. So we can say, okay, so the enclosed charge is just that dude. And this has a distance of 2 pi r, circumference of the circle. And so we have of a straight wire 2 pi r. Okay, and they don't give you this equation, which you should figure out by yourself. Okay, from this, they do give you this. Sorry, with an integral. Good. And the magnetic field is parallel to the line integral that whole time. Like every component's parallel, tangent to that path. Okay? All right. So here, what we have is you need to, so here we've got our Amperian loop. The way that it is positive, you're going to take your alternative right-hand rule and you're going to go in the direction that the black loop is going. That's going to be positive. So these have positive currents. So your thumb is pointing in the direction of the current, and this one will have a negative current. Okay, for the enclosed, the current in the enclosed loop, closing loop. Okay, good. Just yep. Okay. Tell your neighbor. Okay, so we don't worry about this guy. That is just a distractor. So these two are what we care about. It has to have a total 7 amps. So that needs to be going into the page. See. Good?
Does the line integral of B resolution equal something? Like how Gus is like flux, or is it just always going to be called the line integral?
We do have magnetic flux coming, which is the same mathematical application as electric flux. So it's like the field times the area. But no, this is just the line integral. Okay. Tell your neighbor. There we go to B. Okay. This black loop going up, that's positive. Up's positive. Okay. Tell your neighbor. Correct answer is, there we go with B. Okay. Correct answer is, tell your neighbor. Correct answer is A. Okay. Negative. So out of the page will be positive. Tell your neighbor. This is the wire. The direction of the current is going into the page. This is the wire. We're looking on the inside of the wire. Like, we get.
I was thinking that was a big loop, and then there was a wire inside.
Oh, sorry. My bad.
If that little X was gone, we would have all gone.
You think so?
Maybe. It's definitely B other than that.
So we have uniform density. So the whole thing, so this is current over area, yes? Okay. Is equal to, I'm just going to put a lowercase I for like the inside. You right, that? So the current on the inside, ugh. Okay. Yes? See a similar flavor? That density stuff? Yep, tastes about the same. Okay. So, okay, so here's what we can do with that. We want to know, we need to figure out, so we have we've got a wire that has uniform current density throughout it. We can figure out the current outside of that magnetic, outside the wire, but like inside, just like finding the charge on a insulator that has uniform charge density throughout its volume. Okay. So what we've got on the inside, so our Amperian loop is going to be this dude here. And we want to know the charge and charge enclosed. So we just figured out from the previous one that that would be r squared I total over r squared. And this is b 2 pi r. Good as that. So our magnetic field is going to be u naught over 2 pi I over r squared little r. And so we see it is varying linearly as you go from the center to the edge. And then out beyond that behaves just like single wire. Good with that? So that's a very typical free response problem. Okay. Okay, so what happens if the charge density is not constant? We knew that was coming, right? So we have this, a little chunk of current over a little chunk of area. How are we going to divide this up? Specifically, the chunk of area, like I need to know how to splice this out. Like how am I going to divide this? Griffin.
2 pi r d or d.
Okay, I'm going to make my area, it's going to be the area of that ring, which if I cut it out, like fillet it, like whoop, lay it open, I've got a length of 2 pi lowercase r width of dr. How does that sit with you? Good with that? Okay. So, di over 2 pi r dr. Okay. And so j is going to be kr. That's from the problem. Di 2 pi r dr. You okay with that? But when I go to use Ampere's law, I'm looking for the charge enclosed. Can I just plug this straight into that? What is this charge? What is this di? James. Yep, it's the amount of current running through this green, just like through the green part. I need to add up all these little chunks before I can plug it into here. Does that make sense? So, let's do a different color. So I need to set the integral up like di going from 0 to enclosed charge, which is the integral from 0 to lowercase r of 2 pi k r squared dr. Yes? So I get 2 pi k third r cubed. Got that. And then that is what I can plug in here. And so I have magnetic field is equal to, and then this is just 2 pi. Maybe I should be a better teacher here. Be 2 pi r is equal to mu naught times 2 pi k third r cubed. So that knocks that out. That knocks one of those. And so I get my answer to be mu naught k over 3 r squared. Yeah, that's an even better free response problem. Okay. probably the most popular like stumbling block is this part here. Like remembering to integrate, like figuring out it's a little chunk of area, so this make sure this is an area thing, and then integrate that before you stick it in there. Okay. All right. Solenoid has a uniform magnetic field. That's pretty sweet. Um, so yeah, kind of looks like this. Um, so a single loop of wire is going to create a magnetic field that looks like this. Okay, on the outside it's going this way. Everybody all right with that? If you have 3 rings, this is just kind of building up the case. Here, this one's creating B2, this one's creating B1. So it has a little bit going that way. B1 at this point is going that way. And then B3 is from this guy. This guy's also going this way. It's going that way. What it's trying to point out is these pretty much cancel each other out on the outside. But on the inside, they add up. Okay? So this is trying to draw, ideally, magnetic field on the outside is 0. On the inside, it's a uniform. That's an ideal solenoid. Okay? So what we're saying is this, a popular question is, how do you know if it's a solenoid versus multiple rings? Like when can you use this solenoid equation versus rings? And you have n mu naught I over 2r. Remember that we derived that. That's if you have a whole lot more loops, like the length of the loops, like how much of this is big compared to the radius. Does that make sense? Okay. All right, so
Wait, we use that if it's rings or if it's a solenoid?
this is rings.
So like if the radius is a lot less than the length.
If you're like,
Solenoid or
if it's like this, use rings.
so it's really short.
Like the radius is significant compared to how long that is. Rings. If the radius of that is not significant compared to the length, use a solenoid, which we're about to develop here real quick. Okay, so in a solenoid, here's the Amperian loop. Remember with Gauss's law, we had certain shapes that we tried to do the Amperian loop. Sorry, the Gaussian surface. Sometimes you had a cylinder, sometimes you had a sphere. This is the Amperian, the shape of the Amperian loop for a solenoid. This is just a square, okay, or a rectangle. So what we're doing is our enclosed current is however many you're going to capture in that, okay. And since it's one wire, it's just a multiple of however many how many wires you're like capturing in this square. Okay, so the amount of current in or through is just n times what that current is. Okay, now we need to evaluate the line integral of this. So out here, there is no magnetic field ideally. Magnetic field is 0, so there's nothing contributed here. Here and here, also no magnetic field. Once we're inside here, the magnetic field going this way is perpendicular to this part of the Amperian loop. So that part contributes 0. Same as this part here. The only part that has any value is this length here. And it's going parallel to this line integral, this path. So all we say is on this side is just the magnetic field times this length. How are we doing with that? Okay. And then the amount of current enclosed is just N times that. And they do, sadly, give you this. So often, so they'll bring the L over here. This is what's written on the equation sheet. Where N, did I tell you this? N is the number of loops, turns, number of loops, windings per unit length. Okay. I like thinking of it this way. It's, I don't know. But often they'll say you have like 200 or 2,000 loops per meter, something like that. Okay. How are we doing with that? Okay. Another popular shape. Okay. Okay. So technically, the magnetic field of a solenoid is not constant and drops off towards the ends here. Okay, but in an ideal sense, it'll be constant. That's ideally. Okay. Kind of like a capacitor with the fringe fields. Kind of like solenoid, this would be fringe field type stuff. Okay. So here we can see that the diameter is kind of significant to the radius. So it's not a great thing, but ideally it would just be really long compared to that. Okay. And what we're saying is, in these questions, these are all ideal solenoids. Tell your neighbor. Correct answer is? Good question. Just assume it is. If they say solenoid, assume it is.
Assume it's perfect.
If they say if they leave it up to interpretation, they will ask you specifically. Is this a ring? Should we consider this as a ring or as a solenoid? That's the only time you really need to do that. If it like looks like a ring, it's a ring. If it looks like a solenoid, it's a solenoid. They won't like bait you like or they could say, what are some experimental errors? You're like, well, it's not an ideal solenoid. It's behaving a little bit like this. Okay. Correct answer is C. Good with that? Same number of turns per unit length. All right. Everybody good with B? Alternative right-hand rule. Stick your thumb in the direction of magnetic field. Current's going this way. This is on top. Good. Let's see. Hold on a second. Let's see if I want to get into this. There's some more beneficial questions. All right. So, infinite sheet of current. Are you okay with this? Stick our thumb in the direction of the current. It's going this way on top and this way on bottom. Okay with that? Okay. We're like building a case here. Is everybody good to the right? Everybody good with B? This one's contributing to the right. This one is contributing also to the right. Good? Okay. Oh, just already told you. All right, to the right. Okay. About below. Down here. Everybody good. Like infinite sheet. This has magnetic field going all the way forever. Everybody goes zero. Canceling each other out. Down here. This one's creating a magnetic field going to the right. To the right. This one's creating a magnetic field to the left, and they cancel each other out.
Oh, yeah.
Great question. Because it's closer, it doesn't get stronger. If it's infinite, doesn't matter how far you are away. Remember that whole infinite sheet of charge? You're right. You are right. All right. We're going to say all these are ideal, even though they don't look ideal. No. Correct answer is, I'm just going to tell you, D. Cross-sectional area does not matter, so long as it's not a very good. There should be like really long. Doesn't matter. It's easier to wrap in a circle than a square, but it's not. It's not. It's not a have to. All right. Sure thing.
Oh, they all. Before you specified the other one that like it doubled the diameter as well. Do you remember like the one it had the two soles?
That one? Yeah.
And you said that the diameter doubled as well.
Yeah.
Like, does it have to double or does it not have to double?
It doesn't have to.
Okay.
They're just messing with you.
Okay.
Okay. So think we can do this. Think we can do this. Woo, we're gonna try it. Here we go. So we take a long solenoid like this, yes, and we wrap it around to connect the ends. We kind of like bend it. So here we go, and we're gonna like sorta. Okay. So does that make? Is everybody good with that? Okay. Okay. So what this is a torus. Called a torus. Like the car, old car, Ford Taurus. Okay, donut. Okay. All right, so we're going to look at the Amperian loop. This. Okay. All right, so current, three imaginary loops. Path 1, 2, and 3. Okay. Which has the largest enclosed current of 1, 2, or 3. Tell your neighbor. So everybody good with B, 2, because 3 is in and out, canceling each other out. Okay. Me, look at that. Okay, 0, good for that.
We're to assume that there's the same number of wires.
Yep, same going in as going out. So is everybody good with B, like path 2 because of that? Okay. Whoop. All right, path, and this is 0. Yes. Okay. 1 is also 0. Okay. So, what did I say here? With n turns and a current of that. So, we've got the Amperian loop. B 2 pi r is equal to n times I. You all right with that? Okay. So in a solenoid, no, torus. Torus, that's equal to 2 pi Ni over R. Good with that? Okay. And they have these in circuits. Toruses. It's a efficient way to make a space-saving way to make a solenoid.
So why do we have
Why do we have what? Because that it's the same wire. going through this here in one of them. It's the same wire, just wrapped. You too. Yeah. Hey, you got a free response that's due next Monday. I'll throw that up there. It's the current in the one wire that's wrapped a bazillion times. If I Fruit Ninja this thing, this is one wire.
Oh, so yeah, okay. Because I'm thinking in terms of like technically speaking, this is all one wire, right? Yeah.
The free response questions confused me about pivot points. Because I thought for like rotational static problems, you could pick wherever to be the pivot point.
Okay, I'll look at it. I didn't get that far. I got to question 3 or 2. I'll look at it.
Okay. And I was also wondering, this is related, but
Yeah.
is it ever useful to use the gravitational analog gases?
Yeah. Like for electric field versus
For like gravity questions.
for Gauss's law.
Yep.
Yeah.
Play tabs, yeah, play tabs.
Yep. Yep.